All right, so what we need to do today, we'll discuss, we'll go back to this concept of diagonalization that I started referring to at the end of the last lecture. And that's an extremely important topic, and we will continue on that on Wednesday and Friday, okay? All right, so let me just go back to the summary of the lecture today. You remember our eigenvalue problem is AXK equal lambda k xk. So lambda is the kth eigenvalue, xk is the corresponding eigenvector. So if I put all of these eigenvalue equations together, I can actually get a system of equations that looks in this form: AX equal x times lambda. There's really no assumptions involved here. I will show you how this. Basically, by putting all of these equations together, where capital X is a matrix that has one eigenvector in every column, okay? And lambda is a diagonal matrix with the eigenvalues on the diagonal. Okay. So we need to be very clear on this, right? So we don't discuss any specific matrices up to now. So if it happens that the matrix A has n independent eigenvectors, so if it happens that it has n independent eigenvectors, then this matrix X is invertible, and I can write A as x times lambda x minus inverse. Okay? So basically, you remember if the columns are independent, I can invert the matrix. So I can invert X, all right? I can invert X, and I can write A as x lambda x minus 1. And actually, if you look this on a reverse, if you solve for lambda, then you can write lambda x minus 1 AX. And because lambda is a diagonal matrix, effectively what we have done is we have done a transformation to A. We took a general A and we transform it to a diagonal matrix lambda. That's why we call this process diagonalization. Okay? And obviously, when you do computations, it's much more convenient to play with a matrix that's diagonal than a full matrix. So this is an extremely important part of everything in sciences. I mean, all the calculations in hundreds, thousands, millions of problems are utilizing this factorization that we will see it written in many forms in this and the follow-up lectures. All right. So remember, for 2, the only requirement up to now is that we have n independent eigenvectors. And I realize that's a very vague statement. What does it mean, n independent eigenvectors? I mean, a real question would be, and when do I have n independent eigenvectors? So we will postpone this for later, okay? So it's not a trivial question, when do you have n independent eigenvectors? Now, if you have these n independent eigenvectors and you can actually diagonalize a matrix as you see in this equation, or in the earlier equation that gives me A, you can actually take powers of A, and you can, if you take, A times A, which is A squared, so if you take this times A itself, can you see that on the right-hand side, x inverse and x will cancel out? Yep. If you multiply this with itself, right, so you can get A squared, can you see you're going to have x lambda x minus 1 times x lambda x minus 1. So what actually you will get is x times lambda squared x inverse. Yep. So that way you can take powers of the matrix A directly if you know the eigenvalues. If you know the eigenvalues, Okay, hopefully this microphone will be better than the other one. So basically, to take powers of A, what you need to do is take lambda to the power k, and because lambda is a diagonal matrix, lambda to the power k has the eigenvalues to the power k in the diagonal. That's all. It's a diagonal matrix with the eigenvalues to the power k. Now, when we discussed this in the earlier lecture, right? But the whole idea of using eigenvalues and eigenvectors is, in solving problems that change with time, effectively. So address sort of dynamical systems. And here is a matrix sort of representation of a dynamical system, where if I know the state of something at time k, by operating with this matrix A, I get the state at uk plus 1. So you can consider this sort of as an iterative process where you give me the temperature now, and I tell you the temperature in time delta t, and then at time 2 delta t, 3 delta t, and A contains the physics that tells me how I go from time k to time k plus 1. So you can actually see, if you apply this equation repeatedly, you can see that uk is a to the power k u0. Can you see that? Right? What is u1? u1 is a u0, and what is u2 is a times u1, which is a u0, so a squared u0, and you keep going like that, right? And you get uk equal ak u0, and we said ak is written like that. But also we can write this explicitly in the equation that you see here, and we visited this in the earlier lecture on eigenvalues and eigenvectors, where these coefficients c are basically defined by the initial conditions, right? So we need to start from somewhere. We need to know what u0 is. So c1 to cn are being defined from the initial conditions, okay? And the initial conditions are written here in terms of the eigenvectors. So in essence, you notice here, because these eigenvectors are independent, they form a basis of the space that I am working. So I can write any vector, including u0, as a linear combination of x1 to xn. So again, in writing this, I'm using the fact that I have n independent eigenvectors. Otherwise, some of these things may not fly. OK. So generally speaking, okay, if you don't have repeated eigenvalues, you can actually show that you can get n independent eigenvectors if you don't have repeated eigenvalues. This is very important to remember. So if one eigenvalue doesn't come 3 times, all right, you can guarantee actually, if you have distinct eigenvalues, that there is a set of independent eigenvectors, which means that X is invertible. However, if you have repeated eigenvalues, there is no guarantee of anything. And actually, if there are repeated eigenvalues, you may have deficiencies of eigenvectors. And what deficiencies means, you may not have enough actually eigenvectors to form a basis in Rn. You understand that? So, we have n-dimensional space. You say, OK, I'm going to solve the eigenvalues. But you're not going to get n distinct eigenvalues. Some of them will be repeated. If they are repeated, it may happen that the corresponding eigenvectors for a given eigenvalue, they have a different multiplicity than the eigenvalue itself. So let's say lambda equal to 3 comes to be 4 times as an eigenvalue by a miracle. You get lambda minus 3 to the power 4. Okay? There is no guarantee that you will get 4 independent eigenvectors out of lambda equal to 3. You may get 1, you may get 2, you may get 3. If you're lucky, you can get 4, but there is no guarantee. So in that case, the matrix is not diagonalizable, which means X inverse actually doesn't exist. So remember, in general, if you have repeated eigenvalues, you may have a problem because you may not have enough eigenvectors. The good news that will be in the follow-up lecture is that if it happens that the matrix is symmetric, even if you have deficiencies, even if you have multiplicity of eigenvalues, actually you will always have n independent eigenvectors for symmetric matrices. Okay, the proof is actually in the following lecture, so it's not necessarily obvious, but in general, for any matrix A, you cannot actually guarantee that you can get n independent eigenvectors. All right, and and then if I have time, maybe this would be later in another lecture, we're going to define some transformations similarly to what you see up there. So if you have two matrices A and C that they are related through an equation like that, okay, then this matrix C has the same eigenvalues as the matrix A, okay? And so when we have a relation between two matrices C and A like that through a matrix B, we say that C is similar to A. So the word when you hear matrices being similar, it implies basically that they have the same eigenvalues. Okay, so let's go back now. We discussed the whole lecture, so if I don't have time to complete it, no big deal because we already have seen the whole lecture today. So we're looking for a matrix N. So let me go directly. We're going to assume to start with that we have n independent eigenvectors. So in essence, these eigenvectors form a basis for the space Rn. And if they form a basis, means any vector can be written as a linear combination of these eigenvectors. Now, you can, we already have discussed, right, that if you look in, let's say, in a given space, let's say Rn, there are infinite bases that you can select. This eigenbasis, the basis that contains the eigenvectors, is the best because makes everything so easy. Like, you know, you diagonalizes the matrix. I mean, that's wonderful, right? So if actually you do have this basis, this is the best representation, period. Okay? That's the best. All right. So let me see why is this actually really a good representation to have as a basis. So let's say you do a transformation of the form y equal ax. So you know, for every vector x, you operate with a, and you define a new vector y. So y equal ax. So what you do is you represent x in terms of the eigenvectors, and then because a is a constant, it's a linear, it's a linear operation here, I can write this as C1 times AX1 and Cn times AXN. And AX1 is lambda 1 x1, and AXN is lambda n xn by definition of the eigenvalue problem. You see that? So effectively, if you want to actually operate on x with A and define a vector y, if you know the eigenvectors, you already actually know what the answer is going to be. You don't have to do any matrix multiplications or anything like that, because if x is written in the eigenvector basis, y is nothing else but multiply each term there with the corresponding eigenvalue, and you're done. Nice. I mean, imagine if A was a big matrix and you were going to do actually this whole multiplication would be a waste of time, because effectively everything you need is here. Okay? Now, you may say, yeah, but you are cheating us here because that assumes you know the eigenvalues and eigenvectors, and that's very expensive to start with. Yeah, that's true. Okay? I mean, there is no free lunch. Okay. So if we have, so we are basically interested for matrices that have n distinct eigenvalues, so that capital matrix X basically is invertible, okay? And we are going to give a whole lecture on symmetric matrices, because symmetric matrices come with lots of beautiful things when it comes to the diagonalization process. So not only in symmetric matrices you get n independent eigenvectors, but those eigenvectors are orthonormal. And you remember, if you have a basis of orthonormal vectors, even better. So for symmetric matrices, by default, you get basically everything to be orthonormal. Okay? And for symmetric matrices, you don't have to worry even about the multiplicity of eigenvalues, because even in that case, you can prove actually that you can diagonalize the matrix. Okay, even in that case, you can diagonalize the matrix, but for a general matrix, that is not the case. Okay, so we're interested in a diagonalization, so we assume that X is the matrix of the eigenvectors, A is my original matrix, and diagonalization implies that X minus 1AX is equal to capital lambda, where lambda is the matrix of the eigenvalues of the matrix A. Just a little bit about the notation. When you write this diagonalization for any arbitrary matrix, it is good for the notation to use capital X for the matrix of the eigenvectors and reserve a Q there, a Q transpose and a Q only for symmetric matrices to emphasize that they are orthogonal. So for a general matrix, just use a capital X there. Okay, and we already have said if you want to take the power of a matrix M, then basically if you apply the same diagonalization process, you basically get a diagonal matrix with the eigenvalues to the power M. Okay? I don't know about you, but when I was you know, in elementary school, when I was learning these things, I don't know at what time, those days we were learning a lot at a very young age. One of my fascinations was really somebody telling me, what is the sign of this matrix, or the cosine of this matrix? I mean, here you see, you know, you see the power of a matrix, but you will appreciate if you know the power and you think of power expansions, you can actually define the sign of a matrix, the cosine of a matrix, the log of a matrix, anything. So if you have a convergent series in X, you know, in a single variable, you can substitute that with a matrix, and you can define anything you want to. So it's interesting to say, you know, the log of 1 plus A, where A is a matrix, and say log of a matrix? Yeah, why not? And it's extremely useful, actually. All right, extremely useful in a lot of engineering applications. Okay, so let's do one example. We have a 2 by 2 matrix that looks like this trivial little matrix. We computed the 2 eigenvalues, 1 and 6. You can saw the 2 eigenvectors are 1, 0, and 1, 1. So I'm not going to do this simple algebra. By the way, immediately you know that the eigenvalues are 1 and 6. And the reason you know without no algebra is what? Because a triangular, right? So the eigenvalues are directly in the diagonal. Okay? So lambda equal 1 and 6 directly on this problem. All right, so if you actually put the 2 eigenvectors in the columns of this matrix X, that's X, and this is X inverse, okay? You can actually do the multiplication X inverse times AX, and you will see there is lambda, all right? So there is lambda. I mean, the idea here of diagonalization is we are transforming matrix A to something that is much more convenient to work with, and that something is a diagonal matrix. So that's wonderful. So you can think actually of this. You can think of the eigenvectors as the principal directions. All right? So what you do is like the same way in mechanics, you know, you have a stress tensor, you know, and you say these are the stress principal directions or the principal strain directions. Effectively, what do? You rotate to find those new directions where the off-diagonal terms are equal to 0. You have diagonalized your stress tensor or, you know, your strain or whatever, and effectively, trust me, that's what you do. Okay? That's what you do. Of course, you know, different people in different communities, they want to pretend that reinvent things on their own, so they may call different names, but it's really what it is. All right, anything else is not worth discussing it. Okay, and again, the powers, if you want to take the powers of this matrix, so A squared would be X lambda squared X inverse. All right, so let's do a 3 by 3 matrix. Nothing, I don't even know. Usually if there is an example, it means there must be something special, I hope. Maybe no. So let's keep going. So this, if you form the characteristic polynomial, it has 3 roots. So the eigenvalues are 3, minus 4, and 0. And actually, you can test it, because you remember the sum of the eigenvalues needs to be what? A good test. The sum of the eigenvalues is equal to what? Is the trace of the matrix. So if you sum those, right, you get minus 1. Is that what you get? Now I'm in trouble. I told you to okay. 8.3, no, actually, no trouble at all. 7.3, 8.3, minus 9.3, you get actually minus 1. So we're okay. We're okay. All right. So we need to compute the, for each eigenvalue, the corresponding eigenvector. So it's basically the null space solutions. So there are the 3 eigenvectors. So this is my matrix X. This is my matrix X minus 1. And there's the answer. OK? I mean, if we were writing this on the board, I could have spent basically 20 minutes writing all of this, and you have been so happy writing this in your notebooks and say, wow, we learned a 3 by 3. But you know, you look at it and you say, yeah, I understand that. There's no point of spending 20 minutes, OK? I need to respect your time, and I need to respect my time when I teach as well. And you can see again that the eigenvalues here, 3, minus 4, and 0 in the diagonal. So let me prove that, you remember everything started with this equation that I told you early on that comes nothing else but from the assembly of the individual eigenvalue problem. So if you take A capital X, and you write X explicitly in terms of the eigenvectors, so you have AX1, AXN, and then you write each of those as lambda 1x1, lambda nxn, I can take this row vector and write it the matrix capital X times this diagonal matrix lambda, and there is what we're discussing, okay? So AX equal X lambda, or A equal X lambda X minus 1, or the similar equation we had for lambda. Okay. And again, I emphasize we quietly assume that we have n independent eigenvectors. Without n independent eigenvectors, there is no way X minus 1 can be inverted. There is no way you can diagonalize this matrix A. Okay? So n independent eigenvectors. And we talk about the powers. I don't want to discuss this. But let me do an example to show you how easy it is, right? So suppose somebody gives you this matrix. I don't know if you had to do this in the homework, and is asking you, can you find A to the power k? And A to the power k can be A to 55, to power 55. So you know, some of you may go and start multiplying in MATLAB, but look how easy is the calculation, right? So you calculate, you know, we show the matrix X, the eigenvectors, and the inverse of the matrix X. You take the 2 eigenvalues, which are 1 and 6, to the power k, and you do this little multiplication only, and there, here is A to the power k for any k. That's a nice result. I don't know about you, but sort of linear algebra is fascinating, right? A to the power k, there is a closed form solution, no multiplications really, nothing heavy duty. Okay, very easy. Okay, so the only thing you need to use is basically the factorization of, you know, of A, and recognize that A to the power k is X lambda k X inverse. Okay. So I'm going to repeat this because I know when I was taping the last lecture, I was so exhausted at the end of the day. It lasted 2 hours, and my brain kept saying the wrong things without thinking about it. So I need to correct something you're going to hear that I believe I corrected it at the end. But I want to emphasize, any matrix that has no repeated eigenvalues can be diagonalized. Okay? Now, it is possible that a matrix that has repeated eigenvalues can also be diagonalized. But there are no proofs for that matrix unless the matrix is symmetric. Okay? And even in that case, the result is not obvious. But generally, when you see repeated eigenvalues, you have to worry because for a general matrix may imply that actually you cannot diagonalize that matrix. Okay. So let me do one example, okay, of a non-diagonalizable matrix. So we're going to take this matrix 1, 1, minus 1, minus 1. So what are the eigenvalues of this matrix? Or of this matrix, actually, they have the same eigenvalues. What are the eigenvalues? 0, all right? And so you get to basically 0 with multiplicity 2. There's nothing else, okay? So even though the matrix is not 0, you get 0 with multiplicity 2. So will you agree with me? I mean, let's concentrate in one of them. The results will be the same for the other matrix. But will you agree that the eigenvalue that you get, the eigenvector that you get is 1, 1? I mean, that's basically the solution to the null space problem, AX equal to 0. Can you see if you multiply this with 1, 1, you get 0, 0. All right? So can you find me another eigenvector? I mean, this is what we need to diagonalize this matrix, right? We need to have, you know, it's a 2 by 2 matrix. We need 2 eigenvectors that have to be independent. Can you find me another independent eigenvector? The answer is, I don't see it. Okay? So in this case, we basically have only this eigenvector 1, 1. There is shortage, and in this case, the matrix cannot be diagonalized. You can try anything you want to. There is nothing you can do. Now, in linear algebra, right, and especially when you do computer simulations, everything is possible when you play with computers. So I can put in parentheses when I say you cannot diagonalize this, you may change the problem and you say, can you find me the nearest diagonal matrix to this matrix? All right? And there is a solution to that problem, but we will not discuss it here. So I will leave it there that this matrix is not diagonalizable, but for every problem, there is a way around it. Okay? So, but right now, we cannot diagonalize this. Something that I know it came also in the exam, and I don't believe, I doubt it if anybody got it correctly. So let me do two statements. Okay, so we discussed about diagonalizing a matrix, and we said in diagonalization has to do with any independent eigenvectors. So diagonalizing a matrix has nothing to do with inverting a matrix. To invert a matrix, what does that matrix need to have in the context of eigenvalues? You remember if lambda is an eigenvalue of A, what's the eigenvalue of A inverse? Assuming it exists. You remember that equation we had with the powers? You can actually take negative powers as well, right? You can pull things on the other side. And so what's the eigenvalue of A inverse? 1 over lambda. So if I have a matrix, when then a matrix is not invertible? When you have an eigenvalue equal to 0. And now why did I say that this is related with the exam, right? In the exam, I gave you a projection matrix. And you know what a projection matrix does? You might think that this is the column space. It takes a vector from the left null space and projects it to where? To 0. So what every projection matrix is an eigenvalue, what? One of the eigenvalues. We did this actually in the previous lecture. One of the eigenvalues of a projection matrix is lambda equal to if you can find, right, so if you can find an x that when you project it to, let's say, to a column space, you get 0, that to me looks like an eigenvalue problem with an eigenvalue equal to, so Ax equal to 0, right? That's the null space problem. So what is the eigenvalue of that? 0. So that matrix is not invertible, because if there are non-zero solutions to the null space problem, all right, you cannot invert that matrix. Isn't it the whole idea? And if you cannot invert it and it's a square matrix, how much is the determinant of that matrix? But most of you, I think all of you, I want to believe you wrote down as an answer that the determinant of the projection matrix was equal to, what did you write down? What did you write down? Equal to? Come on, guys. Tell me, what did you write down? Nobody will see you. Equal to? What did you write down? There was one problem somewhere says, do this and compute the determinant of the projection matrix. I remember it was question C or something, you know. You remember? You see, you did not even look at it. You did not answer. You say, sorry, we forgot. But the majority of you wrote down that the answer is equal to 1. OK? No, it's 0. All right. Now, let me highlight very fast, right, that if we have if we have distinct eigenvalues, that basically we can have independent eigenvectors. Okay? So let me take the general case of having eigenvalues that they are different from each other, and we'll see that they actually correspond to independent eigenvectors. And I'm going to actually have the proof in general in the follow-up slide, but let me do this for a 2-by-2 matrix, okay? So let me take two eigenvalues, lambda 1 and lambda 2, that they are distinct, so lambda 1 different from lambda 2, and I want to prove that the corresponding eigenvectors are independent. I'm using the equation for independence that says if I take a linear combination equal to 0, the only possible way for this to take place if I have independence is for the coefficients to be 0, right? By definition. So we take this equation, multiply this by a. If you multiply by a, what is a times x1? What is a x1? It's lambda 1 x1. And what is a x2? It's lambda 2 x2. So remember this nice equation. That's one equation if we multiply by a. Take now the same equation that we started and multiply by lambda 2. So you're going to have c1 x1 times lambda 2 and c2 x2 times lambda 2. Then guess what I'm going to do? I'm going to take this equation and that and subtract them. And I'm going to get this wonderful equation. And lambda 1 is not equal to lambda 2. Obviously, the eigenvectors are not 0. Otherwise, we don't bother to even call them eigenvectors. So the only way for this equation to be true is if c1 equal to 0. And similarly, you can show c2 equal to 0. Conclusion, you have a distinct set of eigenvalues. You can immediately show that you get a distinct set of eigenvectors. OK? And on the next slide, there is the proof if you have n eigenvalues and eigenvectors. So you can actually read it, but it's practically the same sort of calculation. I don't know what is particular with this example, but let me go fast in case there is some interesting aspect. So this is matrix A. The two eigenvalues are obviously distinct, 1 and 0.5. You can actually compute the eigenvectors. They are distinct. So you can diagonalize basically the matrix and go from this form to that form. Okay? That's what the theorem says. So there's actually not very much new here. But actually, there is something new here. Okay, now, I covered this on the first lecture. So when you take powers of a matrix, right? So you notice here I have two eigenvalues. I have an eigenvalue 1 and an eigenvalue 0.5. So when I compute the alpha to a power k, and I take k to go to infinity, what is 0.5 to infinity? When you take 0.5 to 1,000 power. So as you keep multiplying 0.5 with itself, what do you get? 0. So the idea here is you get a diagonal matrix here that has only 1 there, okay? So notice something interesting. As k going to infinity, this matrix goes to this matrix. And can you look carefully and tell me what is 0.6 and 0.4? I derived it actually in the earlier slides in the last lecture in a different fashion. But can you tell me now, so when you do this, right, what is 0.6 and 0.4? So A to infinity converges to a matrix that has both its columns equal to what? That eigenvector x1. Everybody can see it? This is extremely important, right? Because you always want to know, if you have a fluid mechanics problem or anything where there is dynamics, you want to know what happens at infinity. And in this case, it actually, you can reason immediately that this matrix to infinity converges to a rank 1 matrix with columns equal, both columns, to the first eigenvector of. Very nice result. You can show this many other ways, the long way, the short way, but it's an exciting result that at infinity, this matrix becomes singular and every column is an eigenvector of A. And of course here, the argument that is essential to discussions of stability that we use is we dropped, in computing AK, we dropped all the eigenvalues that in absolute value are less than 1. So if actually you want at infinity this matrix AK to converge to the 0 matrix, then it needs to have all of its eigenvalues in magnitude less than 1, right? So you can imagine a lot of systems that keep moving and they spiral around the origin and eventually they converge to the origin. You just get the 0 answer. And that has to do with the fact that all the eigenvalues are less than 1, so to some power, they give you 0. Now, you can also appreciate if you have an eigenvalue that in magnitude is greater than 1, then the solution for AK will go to infinity, and that will be an unstable system. OK, let me do one example from Strang's textbook. Really a fascinating sort of application that summarizes a lot of the things we have talked up to now. So I don't know if you are interested in the Fibonacci numbers, but I give you the sequence of these Fibonacci numbers. The first few are 0, 1, 1, 2, 3, 5, 8, 13, etc. And the iterative formula that you use to produce these Fibonacci numbers is that every number is the sum of the previous two numbers. So you can see the third number, 1 is 0 plus 1, 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, 8 is 3 plus 5, etc. So you know what? Somebody will come and say, can you tell me what is the Fibonacci number 100? How are you going to do it? Are you going to start counting? It's like writing a piece of paper, 1 plus 1 equal 2, 2 plus 1 equal 3, 3 plus this equal 5, keep going. And then you will even forget if you are at the 100th number or the 99 because you miss it somewhere in between. How are you going to do this? All right? So here is the idea using our, you remember we always do the computation y equal ax, right? So what I'm going to do is I'm going to write my problem as a matrix eigenvalue problem by defining UK to be the Fibonacci number at k plus 1 iteration, and the second component to be the Fibonacci number fk, right? So this is a vector. I'm defining UK to be this. And then I am writing this update formula in this matrix notation like that. Can you please look at it and convince me that this equation is actually the same thing as that equation? So for example, if you take the second component of this matrix equation, what does the second component tell you? The vector UK plus 1 has what components? Fk plus 2 and Fk plus 1, right? So the second component of this tells you that fk plus 1 is equal 1 times the first component of uk, which is fk plus 1. Doesn't say anything new. It says fk plus 1 equal fk plus 1. How about the first component? The first component of this is fk plus 2. And what is fk plus 2 is fk plus 1 plus fk. 1 plus 1 times uk. You see that? So being able actually to write many problems in such a nice form is substantial for differential equations, right? And in the follow-up lecture, you are going to see lots of approximations with using finite differences. And I'm going to, thinking about it, if I find time, I'm going to give you in the homework due next week for you to actually program this type of things, okay? But right now, my Fibonacci sequence obeys this transition law. So to be able to find now F100, what is the bottom line? What are you going to do? What's the calculation you're going to do? You're going to compute what? If I give you, right, UK plus 1, A, UK, and I ask you to compute the F100, what are you going to do? What do you need to compute? You have to compute the eigenvalues of that matrix because you're going to have to take A to a power, 100 or 99, okay? Depending from where you started. So effectively, the eigenvalues of this are 1 plus minus square root of 5 over 2. And by the way, those are very famous numbers, okay? In case you learned this earlier on in life. But they are very famous numbers, okay? 1 plus minus square root of 5 over 2. They're not coming out of nowhere. That's why people like the Fibonacci numbers. And you can actually show for this matrix the two eigenvectors is right, lambda 1 over 1 and lambda 2 over 1. Okay? You can test it up if you want it, if you don't believe me. Okay? So one eigenvalue, the first one comes with a plus sign, the second one with a minus sign. And before I give you the calculation that will allow us to compute F100, we are going to start with some initial condition, right? In every problem, we start with some initial condition. And for time 0, we need to know F1 and F0. F1 is equal to 1. F0 is equal to 0. So basically, this is my U0. We have to start with knowing two numbers. Because you remember the formula requires basically that you need to know the previous two numbers. So we start with 1 and 0. Okay? That's in my sequence, 0 and 1, sorry. So you can actually show that the vector U0 is equal in terms of the eigenvectors, right? So we're going to write it in terms of the eigenvectors. And you can immediately see from this formula, if you put the two eigenvectors, you can see lambda 1 minus lambda 2 divided by lambda 1 minus lambda 2 gives you 1. And 1 minus 1 gives you a 0. So effectively, the initial condition, it is nothing else but the first eigenvector minus the second divided by lambda 1 minus lambda 2. That's my initial condition, okay? The first eigenvector minus the second divided by lambda 1 minus lambda 2. Okay, I'm done. Because U100 immediately is given by this nice formula. Where did I get that formula? Just let me show you again what I had here. I had U0 equal to this nice thing. How am I going to get U100? I'm going to take U0, and what should I do to U0? Multiply by A to get U1. In the new result, multiply by A to get U2. Multiply by A to get U3. Multiply and multiply by 100 to get U100. So that's my result. A100 minus A100 times x2, okay, from the initial conditions. And can you actually compute this directly? Yes, because the matrix A100 has eigenvalues lambda 1, 100. So A100 has the same eigenvectors as A. So this, the result of that operation is lambda 1 to 1 power 100 x1 minus lambda 2 to the power 100 x2. So that's, I'm done. I'm done. So can you tell me what is the Fibonacci number 100? That's U100. What's the definition of U? What was the first component of UK? Fk plus 1, and the second was Fk. So if I want to compute the 100 Fibonacci number, I need the second component of this vector. And I remind you, okay, if you actually go back, I remind you that both eigenvectors, their second component is equal to 1. That's nice, because if I take the second components of this, what is the Fibonacci number 100 is really lambda 1 to 1 power 100 minus lambda 2 to 1 power 100 divided by lambda 1 minus lambda 2. And how big is the number lambda 2 to 100? You remember this golden number that you get for lambda 2 equals 1 minus square root of 5 over 2. So that to the power of 100, what do you think is going to happen? Is that less than 1 in magnitude? No? 1 minus square root of 5 over 2, how big is that number? It better be less than 1, because that's what I have in the slides. So if it is not, we are ruined, okay? So it better be less than 1, which means U100 is really lambda 1 to 100 divided by square root of 5. And because obviously I took this limit here, there is obviously an approximation because I am dropping this term there, which means because these Fibonacci numbers, actually I should put this should put an F there, not a U, okay? I should correct this and put an F. That's my U vector, this is an F100. So obviously the F100 will be an integer, so it will be the closest integer that you can find to this wonderful number. So that's a wonderful result, right? So you do this Fibonacci numbers, and you can find the 100 number using eigenvalues and eigenvectors. Why not? Okay. All right. So I'm going to go fast because I think this example has something interesting on it. Okay. So it's another example, 3 by 3. So we want to diagonalize. So we take the characteristic polynomial, determinant equal to 0. And I know now why is this a nice example. Because what? What is special about this matrix? What is special? It has a repeated eigenvalue, and that can be bad news. All right? That can be bad news, which it may imply that maybe we cannot diagonalize, because also you will notice this matrix is not symmetric. It's -3 and -1, so there is no guarantee actually that this matrix will be symmetric. So how will you know actually for the simple case? Well, so we have 2 eigenvalues, right? So 5 and -3. So you start with 5. You compute so for the case with 5, you compute the eigenvector. And this is the eigenvector you get, 1, 2, -1. Okay? So for lambda equal to 5, you just compute that. And if you put now on A minus lambda I, you put lambda equal -3, the matrix that you get looks like that. And to find the eigenvectors, you have to solve basically the null space problem that you have actually killed to death up to now. So if you do the row-reduced form, this is what you actually get. This is how the row-reduced form looks like. So can you tell me how many solutions to the null space problem you have, or how many eigenvectors you have for this metric? Say it again. 2. You have 2, which is fantastic, right? So we had an eigenvalue with multiplicity 2, but somehow we can actually, for this problem, we're lucky, we can get 2 eigenvectors. We're lucky. It's not happening all the time, okay? So in that case, we are getting 2. And actually, because the time is passing, let me just tell you, the 2 that we started is called the algebraic multiplicity of that eigenvalue. How many times that eigenvalue appears in my characteristic equation. So in my problem is 2. And then we have another number that's called the geometric multiplicity that counts how many eigenvectors to that eigenvalue I have. And in general, if you have an eigenvalue that appears twice, you can have 1 or 2 independent eigenvectors. All right? But you can have 1 or 2, and that's the geometric multiplicity. So in this case, both multiplicities are the same. And so if you compute the 2 eigenvectors from the null space, you get that. And actually, the whole matrix, I don't know if I have the results. Trust me, if you put the whole capital X matrix, you can see that this thing is diagonalizable. So, and I define here what I just referred to as the algebraic multiplicity and the geometric multiplicity for each eigenvalue. And if the two numbers are not the same, then this difference is called the defect of that eigenvalue. So you have a deficiency. You don't have sufficient number of eigenvectors, all right, to form an n set of independent eigenvectors, and that leads to a matrix that is not diagonalizable.